Everyone knows space is cold, minus 270 degrees Celsius, just 3 degrees above absolute zero. So when China finished assembling its Tiangong space station in 2022, an entire orbital outpost built independently from scratch, the biggest survival challenge for its crew must have been staying warm. 3 humans sealed inside a metal tube, surrounded by one of the coldest backgrounds we know. Here's the thing. That's completely wrong. The real enemy aboard every space station ever built isn't cold, it's heat. And this isn't some quirky footnote, it's the single most counterintuitive fact about living in space, and understanding it changes everything, from why Tiangong looks the way it does, to why the future of space stations might slam into a wall that no amount of money can break through. Here's the physics. Vacuum doesn't cool things down the way air or water does. Vacuum blocks conduction and convection so well that in everyday terms it behaves like an insulator. That's the principle driving everything here, and it comes down to the 3 ways heat can move. Conduction, touching a hot pan, heat flowing through direct contact. Convection, warm air rising off a radiator, replaced by cooler air, creating a cycle. And radiation. Energy streaming outward as electromagnetic waves, the way sunlight warms your face across 150 million kilometers of emptiness. On Earth, conduction and convection do the heavy lifting. Your body heats the air around it. That air rises, cooler air flows in, heat escapes constantly, effortlessly. But outside a space station, there's no air. Conduction needs physical contact. There's essentially nothing to touch. Convection needs a fluid. There's nothing to circulate. That leaves radiation. Infrared waves streaming off warm surfaces into the void. And radiation, at the temperatures humans live at, is shockingly slow. A surface at room temperature, about 300 Kelvin, radiates roughly 460 watts per square meter. That sounds like a lot until you compare it to the thousands of watts conduction strips away per square meter when you plunge your hand into cold water. Radiation is a trickle. Space doesn't suck heat out of you. Space makes you work to get rid of it. That's the conceptual spine. Vacuum is a thermos, not a freezer, and it governs every engineering decision about keeping humans alive in orbit. Now think about what's packed inside a space station. 3 human bodies, each putting out roughly 100 watts of heat, the same as 3 incandescent light bulbs burning around the clock. Add dozens of computers, experiments, life support pumps, communication systems, all converting electrical energy into waste heat. The ISS generates on the order of tens of kilowatts of thermal waste, often quoted around 70 kilowatts at peak operation. Tiangong generates less, but from a much smaller structure with much less surface area to radiate from. On Earth, none of this matters. Open a window. Run a fan. Let the atmosphere carry it away. But seal those systems inside a vacuum-surrounded shell, inside a thermos, and the heat piles up with nowhere to go. Without active cooling, cabin temperatures can climb minute by minute. Within hours, it becomes lethal. Not from freezing, from cooking. So here's your first challenge. Picture a taikonaut outside Tiangong during a spacewalk, floating in the station's shadow, no direct sunlight, surrounded by what every documentary calls the freezing void of space. Now imagine, just hypothetically, they briefly expose a bare hand to this environment. What happens? Think about what the physics predicts. Use the thermos principle. Take a second. Most people imagine instant frostbite, skin flash freezing on contact with temperatures hundreds of degrees below zero. But that intuition is built entirely on Earth experience, where air and water conduct heat away fast. In vacuum, there's no air to conduct anything. No wind driving convection. Heat can only leave the hand by radiation and by a brief violent form of evaporative cooling as surface moisture starts flashing into vapor in the low pressure. Even with that, it still doesn't turn your hand into an ice cube in seconds. The hand would cool, yes, but not the Hollywood way. Over minutes, not instantly. And long before in the vacuum of space, the real danger isn't freezing, it's boiling. The thermos holds your heat while the vacuum attacks your pressure. Everything about the popular image of space is inverted. This understanding wasn't handed down from theory, it was learned the hard way. In 1962, during NASA's Mercury program, Scott Carpenter orbited Earth inside Aurora 7 and reported something mission controllers hadn't expected the public to find intuitive at all. He wasn't cold. His suit temperature was climbing uncomfortably high. The compact capsule, absorbing sunlight on its sun-facing side while containing a working human body and warm electronics, generated heat faster than it could radiate the excess into space. The same problem surfaced repeatedly through the Gemini program. Astronauts on several missions reported significant discomfort from overheating during orbital operations. NASA's thermal engineers were forced to pivot their entire design philosophy from keeping the crew warm to dumping enough heat into a vacuum that refuses to take it. The answer, still used aboard every crewed spacecraft today, is the pumped fluid loop. Inside the station, cool water circulates through heat exchangers and cold plates, soaking up warmth from equipment and cabin air. This heated water transfers energy to a second loop, often ammonia on large spacecraft, chosen because it won't freeze at 0 degrees Celsius and when pressurized stays liquid over the temperatures spacecraft plumbing actually sees. The ammonia then flows to large external radiator panels, flat surfaces facing the darkness of space, where heat slowly bleeds away as infrared radiation. Those long white panels visible on the outside of the ISS that people sometimes overlook next to the solar arrays, those are radiators, hundreds of square meters of surface area dedicated entirely to rejecting heat. Without them, the ISS would become uninhabitable in a matter of hours, not from cold exposure, from thermal runaway inside a thermos. And that brings the story to China, not as a political narrative, but as a physics one. Because when Chinese engineers set out to design an independent space station from scratch, they faced the thermos problem with fresh eyes and different constraints. China didn't choose to go it alone. In 2011, the United States Congress passed the Wolf Amendment, prohibiting NASA from bilateral cooperation with China's space program. The door to the International Space Station was closed. So China's engineers built their own orbital laboratory from the ground up. Tiangong, meaning Heavenly Palace, was assembled in orbit between April 2021 and October 2022, module by module. Tianhe Core Module first, then the Wentian and Mengqian laboratory modules, forming a T-shaped configuration totaling about 66 metric tons, 1/6 the mass of the ISS, room for 3 crew instead of 6 or 7, and a thermal control architecture shaped by a subtly different orbital geometry. Here's a prediction question most space engineers find surprisingly tricky. Tiangong orbits at 41.5 degrees inclination, the tilt of its orbital plane relative to Earth's equator. The ISS orbits at 51.6 degrees. Both fly at roughly 400 kilometers altitude. Which station faces more extreme thermal challenges? And what could the angle of an orbit possibly have to do with heat? Think about it before moving on. The obvious guess, the ISS, because its orbit covers a wider range of latitudes, captures the right intuition but the wrong mechanism. What actually matters is something called the beta angle, the angle between the station's orbital plane and the direction to the Sun. As Earth moves around the Sun and seasons shift, the beta angle changes. At high beta angles, something dramatic happens. A station can spend nearly its entire 90-minute orbit bathed in continuous sunlight. No passes through Earth's shadow, no thermal relief, just relentless solar heating piled on top of internal waste heat. The ISS, with its steeper inclination, can reach more extreme high beta conditions. During these periods, more than 70 of every 90 minutes can be spent in direct sunlight, and at the most extreme beta angles, eclipses can disappear entirely. The thermal control system strains near its maximum, radiator arrays rotate to optimize their angle to dark space, and mission controllers sometimes delay power-hungry experiments to keep the heat budget balanced. Tiangong's lower inclination generally limits how extreme those continuous sunlight seasons get, a genuine thermodynamic advantage baked into its orbital choice. But the trade-off is that Tiangong has proportionately smaller radiators and tighter thermal margins. Chinese controllers compensate by actively managing power loads, dimming non-essential systems during high heat periods. The ISS brute forces the thermos problem with massive radiator area. Tiangong manages it with orbital geometry and scheduling discipline. Different engineering, same underlying physics. This reveals something most people never consider. The thermal budget isn't a background engineering detail, it's the fundamental constraint on what a space station can do. Every watt of electricity powering every experiment eventually becomes waste heat. Every watt of waste heat needs radiator surface to escape. When Tiangong's mission planners decide which experiments run simultaneously, the calculation isn't just about power supply capacity, it's about whether the radiators can reject the heat that combination generates. Exceed the thermal budget, and the station slowly cooks from the inside. The thermos problem, the same principle from the opening, dictates daily life in orbit. This same physics shadows every crewed vehicle ever built. During Apollo 13, after an oxygen tank explosion crippled the command module, the crew sheltered in the lunar module with most systems powered down. Interior temperatures dropped to about 4 degrees Celsius, not because space was sucking heat through the hull, but because with electronics off, internal heat generation fell below the rate of radiative loss. The thermos was still a thermos. But with the heater turned off inside, even a thermos slowly cools. Same principle, opposite side of the thermal balance. Spacesuits show the problem at its most personal. An astronaut doing hard physical work during a spacewalk generates around 300 watts of metabolic heat. Add direct sunlight heating the suit's sun-facing surface to around 120 degrees Celsius, and the thermal load spikes dangerously. Every spacesuit since the Apollo era has included a liquid cooling garment, essentially long underwear threaded with narrow water tubes pressed against the skin. Cool water absorbs body heat, carries it to a sublimator in the suit's backpack, where water is fed into a porous plate, freezes, and then sublimates into vacuum, carrying energy away. Without this system, an astronaut would overheat within about 15 minutes of strenuous work. The spacesuit isn't a coat keeping cold out, it's a wearable air conditioner pushing heat out. Once more, the thermos problem in miniature. Now, the future, and one final test of the principle. China has announced plans to expand Tiangong over the coming decade. Commercial companies, Axiom Space, Vast, Orbital Reef, are designing stations that could rival or exceed the ISS in size. The ambitions are enormous. Orbital hotels, pharmaceutical manufacturing, deep space staging platforms. Every one of these projects runs headfirst into the thermos problem at a scale that exposes a deep mathematical wall. Suppose someone wants to build a space station with 10 times Tiangong's habitable volume, 10 times the crew, 10 times the experiments, roughly 10 times the waste heat. How much bigger do the radiators need to be? Pause and think about the geometry. The answer comes from one of the oldest scaling laws in science. Internal heat generation scales with volume. More people, more equipment, more power, all producing waste heat roughly proportional to how much stuff is packed inside. But radiator capacity scales with surface area, and geometry guarantees that volume grows faster than surface area. Double the linear dimensions of an object and volume increases eightfold, but surface area only quadruples. This is the square-cube law, and it means the ratio of heat generation to heat rejection gets worse as a station grows larger. This is the same law that explains why elephants need enormous ears, proportionally far larger than a mouse's, to shed metabolic heat. Biology hit this wall billions of years ago and arrived at one universal solution: distribute the cooling. Capillaries, not one giant vessel. Many small radiating surfaces, not one large one. For space stations, this means a 10 times bigger station needs about 10 times the radiator capacity. And if you try to get it by simply scaling one big habitat, the available surface area doesn't come close to keeping up. So the radiators have to grow disproportionately relative to the living space. At some point, a station becomes more radiator than habitat. Engineers are already exploring solutions: deployable radiator membranes, higher temperature loops using specialized working fluids. But nothing cheats the Stefan Boltzmann law. Nothing escapes the square-cube relationship. The vacuum remains a thermos. This might be why China's modular architecture is thermally smarter than it first appears. Each new module brings its own thermal loops, its own radiators, its own heat budget. The station grows as a network of small thermoses rather than one expanding thermos, dramatically softening the square cube wall. It's the capillary strategy. Whether or not Chinese engineers chose it specifically for thermal reasons, the physics rewards it. Step back for a moment and feel the scale of what this principle governs. The same thermodynamic struggle playing out inside Tiangong, generating heat on the inside, fighting to radiate it from the outside, is the fundamental story of every luminous object in the cosmos. The Sun is a thermonuclear furnace wrapped in vacuum, pouring energy from its surface, according to the same Stefan Boltzmann law that sizes Tiangong's radiator panels. And that radiation doesn't flow into a static stage. The universe is expanding, and dark energy is accelerating that expansion. But the extreme what observations favor is a gentler big freeze, continued expansion with dark energy staying roughly constant as everything thins out and cools. In that far future picture, the universe doesn't go silent because For context, our Sun is only about 7 times wider than Proxima Centauri. And it's also much hotter at the surface, which is why it can radiate so much more power into space. Its thermal control system is simply its enormous surface area. Earth absorbs that solar energy and re-radiates it to space in a delicate balance. Tip that balance even slightly, trap a fraction more outgoing radiation with greenhouse gases, and the planet warms. That's climate change in one sentence, the thermos problem at planetary scale. Every star that shines, every planet that holds a temperature, every space station that keeps a human alive, all managing the same negotiation between energy generated inside and radiation escaping outside. So the next time someone says space is freezing and astronauts must be bundled up against the cold, you'll know the real story. Space isn't cold. Space isn't hot. Space is empty. And emptiness turns out to be the most dangerous thermal environment imaginable, not because it steals your warmth, but because it refuses to take it. Every space station circling Earth right now, from Tiangong to the ISS to whatever comes next, is a sealed thermos with humans inside, fighting to push their heat out through the only channel physics allows, the slow, patient glow of infrared radiation streaming into an infinite void. The vacuum doesn't care about flags or budgets or rivalries. It asks one question: can your radiators keep up? For now, they can, but as humanity builds larger, reaches further, and dreams of permanent cities beyond this planet, that question will only get harder, and the answer will always come down to the same quiet law that lights every star and warms every world: how fast a warm surface can glow into an empty universe that refuses to take its heat any other way. Like if this was interesting, hit the subscribe for more, and turn that notification bell on.